And the point of this is it's the same as 2D. Okay, so let's say that we have a plate that's connected to the wall by like a pin joint type thing. And I'll draw that in more detail in a second. Okay, but this this joint lets it rotate like this, but doesn't allow any other type of motion. And let's say that the lengths are 0.4 meters, 0.6 meters, and let's say that it's also the point right there on the edge is connected to the wall directly above the corner. And let's say that it's up 0.3 meters. And let's say the mass of the plate is 200 kilograms. What are the reactions? No. That won't come into it. All right, so this is like a, you can think of this as a hinge that prevents all rotation. Oh, sorry. It prevents all motions except rotation about its axis. So that means that if a force was applied to the side here, this hinge joint would keep it from sliding. Okay. If you tried to take this and pull it this way, it would keep it from rotating that way, right? If you tried to twist this side up and this side down, it would keep it from rotating that way. And it prevents translation this way and that way. Okay, so let's think about what kind of reactions in 3D are provided by a joint like that. Remember that when we talked about joints in 2D, I gave you like all the rules for the different joints. But then at the end, I said, if you forget the rules, you can always remind yourself what reactions a joint provides by what motions are restricted, what motions are prevented. Okay. So let's choose a coordinate system. I guess I'll put it right at the center. And so let's say the x-axis goes this way, the y-axis goes up, and the z-axis goes to the side. And now let's think about components of the reaction. Okay. So we're going to think about the reaction loads at the hinge. Okay. So first, is translation allowed? So think of the points that are connected to this hinge. Is translation allowed along x, y, or z axes? So just think of pulling this thing along x, pulling it along z, pulling it along y. Can you move any of those points? Those are all prevented, okay? And so therefore, this joint provides a reaction force vector I'll just call it Rx, Ry, and Rz. Okay. So now let's think about the rotations. What about a rotation about the z-axis? Is that allowed? That's the one that is allowed. Do you see that? The z-axis is parallel to the axis of that hinge. And so this thing can rotate this way. Okay. What about a rotation about the x-axis? That would be like what I said, where you take this side, push it up, pull this side down. That's not allowed. Okay. What about a rotation about the y-axis? That's not allowed. That would be like trying to rip this off the hinges this way, you know? So is rotation allowed about the x, y, or z axis? Only the z-axis. So this provides a couple mx, my, 0. Okay? You follow that? All right. What?
That's like a variable that's provided some type of friction when they're moving along the z-axis.
So if it's in static equilibrium, yeah, you just have to determine whether that, so is it in static equilibrium only because the friction is there, or without the friction there? You have to decide which way you want to treat it. If you're depending on that friction to provide the force that keeps it in equilibrium, then you include it. Otherwise, yeah. Okay, so the free body diagram looks like this. We have a force vector R, and we have a couple with a component in the y direction and a component in the x direction. So this is our M. Okay, or if you're writing two of those components, you could write it as this is our my component and this is our mx component. And then there's also a force vector due to that cable tension. We'll express that in terms of the unit vector, but there's that force. And then there's also a weight force acting down from the middle. I guess I'll write that. How do I want to do that? just to show that it's not acting at the edge there. So that'll be 1962. The mass was 200 kilograms. That cable tension, well, we have to come up with, so notice what a nightmare this would be now that we've gone to 3 dimensions to try to come up with this in terms of an angle first. You'd have to have angles about multiple axes. Clearly the way to do this is to come up with coordinates for this point, coordinates for this point, subtract them and figure out the unit vector. Okay, that's just always the case in 3D. So what are the coordinates of this attachment point for the cable? So it would be for x, negative 0.3, right? And then for y, positive 0.3, and then for z, positive 0.2. So for the cable, we have negative 0.3, positive 0.3, and positive 0.2. And what are the coordinates of this point? Just positive 0.3 and everything else is 0, right? So you can think of this as like a vector in the right direction. So we have negative 0.6, positive 0.3, positive 0.2. That's not a unit vector though. Yep. So the magnitude of this vector is 0.6 squared plus 0.3 squared plus 0.2 squared, all square root. So what do you get for that? Can someone? Just 0.70. And so then the unit vector the unit vector is negative 0.6 over 0.7, positive 0.3 over 0.7, and positive 0.2 over 0.7. So what do you get for the unit vector? Okay. Okay. And if you took the magnitude of this unit vector, what would you get? Yes. All the rest of you are not listening appropriately. Okay, so what's the force vector applied by that cable? The force is, yep, that's exactly right. So negative 0.857 T, 0.429 T, 0.286 T. Okay. Okay, so now we can set up the table. And everything with the table works the exact same way. So pancake, artist, row, 4, marzipan. We have to deal with these couples and 3 forces. So let's start with that cable force we just calculated. What are the coordinates where that cable force is applied? Yep, that's this one. So at the point 0.300. Might as well use the origin as the about point. So the row vector is 0.300. The force vector is this, so negative 0.857t, positive 0.429t, positive 0.286t. And what do you get for the moment? Well, just take the cross product of this and this. You know, now you're going to have multiple components instead of just a z component, but it works the same way. Can someone take that cross product? So you'll have 0x component. You guys do the other two.
Negative
0.128. Okay, t. Okay, so anyone get something like that? And now the weight force, that acts at the origin. About point is 0. Row vector is 0. That is in the negative y direction, so we have 0, negative 1962, 0. No moment. Then what do we still have? The reactions. So what are the coordinates where this reaction occurs? It acts. Yeah, so negative 0.300. So the row vector is negative 0.300. The force vector is Rx, Ry, Rz. And there's no moment. And then the last thing is that couple, that reaction couple. We don't care about any of this. And the components are mx, my, 0. Okay, so Newton's second law says negative 0.857 t, positive 0.429 t, positive 0.286 t, plus 0, negative 1962, 0, plus Rx, Ry, Rz is equal to zeros. And the rotational equation says 0, negative 0.857 t, positive 0.128 t, plus mx, my, 0 is equal to 0, 0, 0. Yep.
Isn't there a moment for the reaction force?
Yes, sorry. I just got excited. So one more moment in there. What do you get when you? Okay, negative 0.3 RZ and positive 0.3 RY. The negatives are switched. Okay. Oh, not point. There should be a 0 here. Okay. And so then add in that last one. Oh, okay. I thought there were more problems. I'm sure there are. So 0.3 RZ negative 0.3 RY. Add those up, equals 0. Okay, so now what we have is in 2D problems, for a rigid body problem, we always have 3 equations and we need to have 3 unknowns. Here we have 6 equations and the variables are 1, 2, 3, 4, 5, 6. Okay, so we have 6 equations for 6 variables. If you write out the table, write out the matrix and solve that, you can solve it. Like, so, and let's not even, I don't think it's even, there's any need to do that, but I just want you to notice that everything about the approach works exactly the same. Obviously, it's a much more major headache to think in 3D and to come up with all those unit vectors, and thinking about the reactions provided by a joint are a little more confusing, but all of the basic ideas, including the way the table works, all work still in 3D. And that applies with structures too. Like you could have structures where you have ball and socket joints everywhere, and obviously like the number of equations and variables just goes up so fast, but all these approaches still work. Any questions about that? Okay, well, we have office hours now, and so in the morning, yeah, I can be here. I can be here at 11 tomorrow. So yeah, I'll just open that same 1320 if you want to come in the morning and ask questions.